This research is really motivated by the prevalence of congenital heart disease. So nearly 1% of births have a congenital heart disease, and in particularly severe cases, there's no real cure. We just have these palliative surgeries that allow the kids to survive, but not necessarily to thrive. So we're really motivated by trying to improve those outcomes. So we try and use computer models that incorporate imaging data from CT scans or MRI, as well as data gathered during their surgeries to develop computer models that predict what happens as the disease progresses so that we can discover new treatments and plan better treatment options for those kids. This is really important because the kids, even though their surgery has corrected the congenital heart disease, they still have long-term complications. So the surgery is palliative, they have exercise inefficiency, so they can't go out and run and play like a normal kid necessarily, as well as improve their lives as adults. Once late in the disease, they start to have complications like heart failure, they need transplants. So we try and predict when they would need a transplant, how to improve the transplants that they receive, and make sure they live normal and long, healthy lifespans. So one of the exciting things that we've already published with this and is already in clinical trials is to develop tissue-engineered vascular conduits for kids specifically who are born with a single ventricle heart defect. So only one side of their heart functions properly. And so they need these vascular grafts to use as part of the surgery. And so these grafts are implanted when the kids are only 2 or 3 years old, and the current clinically used ones don't grow over time. So we work to develop tissue-engineered grafts that were able to grow with the kids over time after they were implanted. And so I used computer models to try and aid in the design of those grafts and prevent long-term complication that can occur with the implantation of these tissue-engineered grafts. The next steps with these grafts is to try and improve them both for their current applications, so explore a lot of the new materials that have come out in the past 10 years with advances in material science and fabrication technologies, as well as to expand them to new applications like for coronary artery bypass, which is one of the most common surgical procedures and still results in a lot of long-term complications with those grafts. Another really interesting direction that we hope to take this project is looking at the pulmonary vasculature. So in the lungs, the blood vessels also change a lot during congenital heart disease because with changes in the heart structure, you have changes in the loads that the lungs experience both before children are even born and then as they're growing. So we hope to use our models, which predict time courses, to predict what's happening through the lungs during development, and then how we can prevent adverse changes in the lungs that will eventually cause problems for these kids. So one of the main challenges is gathering enough data that we can build accurate computer models and also have data for validation. This data comes from many different sources, both the clinic and experimental tests. And so what we're really trying to do is move into doing our own biomechanical and imaging experiments so we get the kind of time course data through disease development that will let us make sure our models are accurate and be able to verify their results. We're really trying to predict the time course of cardiovascular diseases using computer models so that we can predict what's going to happen to patients and then also design and improve the current treatments that are available for them.